There are times, however, on this graph, as I've already said, that the temperature does not change, or the phase does not change rather. Instead, we have temperature changes at 1, 3, and 5. All right. So remember, you either have a phase change or you have a temperature change. We've already talked about phase changes, and this is the equation for a phase change. If you have a temperature change, it's a slightly different equation. So look at the top of the last page, and I'm going to go to the PowerPoint presentation we had for temperature change. If you have a temperature change, your equation is this: Q equals mc delta T, or sometimes known as MCAT. Q equals MCAT. Fun sounding equation. Q, as we already said before, is heat energy. In this case specifically, it's the thermal energy that will be added to or taken away from an object, because we're talking about changing temperature. So we're either adding energy or taking away energy. Sometimes it can talk about energy that's stored in an object, but that's something different entirely. That's calorimetry, and we don't really get there in this course. M, of course, is mass, and it's in kilograms like it always has been. C is a new variable called specific heat that we'll talk about specifically, pun intended, in just a moment. The units for specific heat are very, very important to know. You need to know that the units for specific heat are joules per kilogram Kelvin. And then delta T, as you might have guessed, is change in temperature. And here's the fun part about change in temperature. For the first time all year, you don't have to change the units for change in temperature. It can be either Celsius or Kelvin. And the reason why is because remember that we talked about Celsius and Kelvin, and the two scales are the same scale. In other words, the distance between 1 degree and the next is the same. So as long as the two temperatures that you're given are in the same units, be it Celsius or Kelvin, the temperature change is going to be the same. Just the same as changing from 0 to 100 Celsius is the same as going from 273 to 373 Kelvin. And now specific heat. You need to know, it's very important, that specific heat is the amount of heat required to raise the temperature of 1 kilogram of any substance 1 degree Celsius or Kelvin. So I take 1 kilogram of any substance and I want to raise it 1 degree Celsius or Kelvin. And depending on the substance, that task is going to take a different amount of heat. And if we look at this table of substances here, we have water, ethanol, aluminum, and gold, and their specific heats. And if I ask you this question, which substance will heat up the fastest? Think about that for a minute and choose your answer. All right, I hope you've chosen the correct answer would be gold. Gold would heat up the fastest, and the reason is this. If I have 1 kilogram of gold and I want to raise its temperature 1 degree, I only have to add 126 joules of heat to do that. As opposed to the next question, which substance will heat up the slowest? Well, the answer to that, of course, is water. Water heats up the slowest. In fact, you need to know that water has a notoriously high specific heat, which means for the same mass of water, 1 kilogram, to raise it the same amount of temperature, 1 degree Kelvin or Celsius, I have to add not 126 joules, but 4,180 joules of heat. Same task, different substances, quite a different requirement of heat. Okay, so the specific heat is a very important factor, and you need to know how that changes things. And let's look back at the notes here for a minute. All right, here in the notes you should have filled all this in from the PowerPoint that I showed you, and I want to talk to you about this little flow chart. High C, not talking about the drink, I'm talking about a substance with high specific heat. You need to know that the most notoriously high specific heat for a substance is water. Right? Water has a high specific heat, and that means that water is going to heat very slowly. It takes a long time for water to heat up, and it also takes a long time for water to cool down. Heats and cools very slowly. The reason why is because it requires a lot more energy to heat and cool. It requires more energy because it will absorb more energy when it heats up, and when it cools down, it will release a lot more energy when it cools down. All right, so that's water. And low specific heat, a substance with notoriously low specific heat is air itself, water and air. Air, as opposed to water, dry air, heats up very rapidly and it will also cool very rapidly. And the reason why is because it requires less energy to heat up, it absorbs less energy when it heats up, and it will release less energy when it cools down. High specific heat, low specific heat. Great example of this is an arid environment like a desert versus a tropical or more humid environment, maybe like San Francisco. Right? San Francisco has a very moderate climate, tropical rainforest. The thing that characterizes those climates is not as much heat as it is that the temperature, whatever it is, stays very constant. And the reason is because the water in the air takes a long time to heat up. And when it does heat up, it takes a long time to cool down. The effect of that is that the temperature doesn't change very much in those areas. It's very moderate, it's very stable. Because water requires a lot of energy to heat up, and when it does heat up, it releases quite a bit of energy. As opposed to a place like a desert, Tempe, Arizona, not very much water in the air, so you just have a lot of air, and air itself has a low specific heat, therefore it will heat up very rapidly. When the sun comes up in the desert, it gets very hot very quickly, and there should be an L right here. And then when the sun goes down, it cools off really quickly. So in the daytime, a desert gets very, very warm, above 100 degrees Fahrenheit sometimes, and at night temperatures can fall below freezing quite regularly because air itself has a low specific heat. There's not very much water in the air. Low specific heat substance requires less energy to heat up, doesn't have to release very much energy to cool down. Think about your swimming pool. When the temperatures outside begin to warm up, say end of April, early May, you may think it's warm enough to go jump in the pool, but if you do that, you might get a very chilly surprise because your pool itself is still very cool. The reason is because the water in your pool has a high specific heat, and it takes a long time for it to heat up. It's not until about June that you get some really comfortable swimming weather because the water has heated up to that point where it's not just bone-chilling cold when you jump in. And then conversely, at the end of the summer, when your pool is 94 degrees and nobody wants to jump in, it stays 94 degrees sometimes through September, October, maybe even November. And the pool itself will many times be warmer than the outside air itself because water takes a long time to cool down because there's a lot of energy contained in that water. And to cool down, it has to release quite a bit of energy. So those are the main differences between substances with high specific heat and substances with low specific heat. Alright, so you should have written Q equals mc delta T here. And I want to think about that equation to answer this question. Think about this. You have two blocks of lead. They have the same temperature. We heat them up to the same temperature. Block A has twice the amount of mass that block B does. We drop them into identical cups of water of equal temperature and equal mass. I want to know, will the two cups of water have equal temperatures after thermal equilibrium is reached? After all the heat has been exchanged between the lead and the water, will they have equal temperatures? Think about that for a second. Pause the video. Alright. Many of you may have said that they will be different, or the same temperature rather, and they'll be the same temperature, and your reasoning is because the blocks and the temperature all started at the same temperature. Right? But the answer is actually that no, they will not have the same temperature. The cup, so cup with block A will have a higher temperature. Whatever cup block A went into, since it has twice the mass, it will have a higher temperature. And here's the reason. Let's look at this equation. Q equals mc delta T. Remember what I said about the cup of water versus the bucket of water. They're both at the same temperature. Therefore, a thermometer will read 90 degrees both times, right? But clearly, when I look at this equation, it's clear to see that the bucket has a higher amount of thermal energy in it because it has a higher mass. It has more Q, more heat energy. And it's the heat energy that's going to be transferred to the substance to change the temperature. the temperature doesn't directly get transferred. The change of temperature is a result of heat energy getting transferred, right? So the reason why the cup that has block A in it will have a higher temperature is because block A had a higher mass. We had more mass, and since there's more mass, there's more heat energy to be transferred to that cup of water. So the cup that has the bigger block in it is going to end up with higher temperature because block A has more heat energy, more Q in it to contribute. Let's do a couple of problems. A couple of temperature change problems. I'm going to do, well, let's do one of them actually. Let's do number 4, right? I'll leave number 3 and number 5 to you. These are the correct answers, and you can see if you got those right by checking your answer there. Keep in mind that when you put things like this into equation, remember that Q, heat energy, has to be in joules. All right? That's a hint. Number 4. A 0.4 kilogram block of iron is heated from 295K to 325K, and we want to know how much heat had to be transferred to the iron to do that. Well, let's look at what we're given. Hopefully you know that this is the mass, and we don't have to convert that. It's already in kilograms. 450 joules per kilogram Kelvin. I hope you can realize that this is C, the specific heat. And you only know that because you should know the units for specific heat, which are joules per kilogram Kelvin. It's heated from 295K to 325K. That is the change in temperature, which would be 325 minus 295. And that gives me a temperature change of 30 degrees Kelvin. Right? How much heat had to be transferred? I'm looking for Q. And now I should know, well, I need to back up actually, because when I read these problems I need to determine phase change or temperature change, and since they gave me 2 different temperatures, pretty good key that you have a temperature change. And the equation for temperature change is the MCAT equation, Q equals MC delta T. So we just plug in what we know and solve for what they want, right? So mass is 0.4, C is the specific heat, which is 450, and change in temperature, we calculated 30 degrees Kelvin. Right? So if you multiply all that together, you'll find that you do get the answer that they have, which is 5,400 joules of heat energy. Work number 3 and number 5 on your own, and then hopefully that'll give you what you need for at least the front side of the homework. The back side of the homework is about thermodynamics, and I'll discuss that in another video.